Voltage drop in three-wire feeder panels is a crucial consideration in electrical system design. It essentially refers to the reduction in voltage that occurs along the conductors from the source to the load. In a three-wire system consisting of two hot legs and a neutral, voltage drop can manifest in several ways, potentially leading to what might be considered an objectionable outcome. Firstly, it's essential to understand how current flows in a three-wire system. When balanced loads are connected between each hot leg and the neutral current is theoretically zero. However, in reality, loads are rarely perfectly balanced. This imbalance results in current flowing through the neutral conductor. This neutral current, coupled with the impedance of the neutral conductor, contributes to voltage drop. Secondly, the impedance of the conductors themselves plays a significant role. Impedance is the total opposition to current flow in an alternating current circuit encompassing both resistance and reactance. Resistance is the opposition to current flow due to the material of the conductor, while reactance is the opposition due to the inductance and capacitance of the conductor. Longer conductors, smaller conductor sizes, and conductors with higher resistance will all contribute to greater voltage drop. Thirdly, the load current itself is a primary factor. Higher load currents will naturally cause a greater voltage drop across the conductors. This is a direct application of Ohm's law, which states that voltage drop is equal to the current multiplied by the impedance. The effects of excessive voltage drop can be multifaceted. One notable consequence is reduced performance of connected equipment. Motors may not start properly or may run at reduced speed, lighting may be dimmer than expected, and electronic devices may malfunction or operate unreliably. Sensitive electronic equipment may be more susceptible to damage due to voltage fluctuations. Furthermore, excessive voltage drop can lead to overheating of conductors and equipment. This is because the power dissipated as heat in a conductor is proportional to the square of the current multiplied by the resistance. Higher voltage drop implies higher current or higher resistance, both of which contribute to increased heat generation. Overheating can degrade insulation, reduce the lifespan of equipment, and even create a fire hazard. The National Electrical Code, or NEC, provides guidelines for minimizing voltage drop in electrical systems. While the NEC does not explicitly mandate a specific voltage drop limit for all applications, it does recommend that voltage drop on feeder and branch circuits should not exceed 3% for power, heating, and lighting loads or 5% for feeders plus branch circuits to the farthest outlet. These are recommendations, not mandatory rules, but they serve as a benchmark for good design practice. Several methods can be employed to mitigate voltage drop in three-wire feeder panels. Firstly, increasing the conductor size reduces the resistance and impedance of the conductors, thereby reducing voltage drop. This is often the most straightforward and effective solution. The appropriate conductor size can be determined using voltage drop calculators or tables provided in the NEC, such as those found in Chapter 9. Secondly, shortening the length of the conductors can also significantly reduce voltage drop. This may involve relocating the panel board closer to the loads or using multiple panel boards to distribute the loads more evenly. Thirdly, using conductors with low resistance, such as copper instead of aluminum, can also help to minimize voltage drop. Copper has a lower resistivity than aluminum, meaning it offers less resistance to current flow for a given conductor size. Fourthly, for long runs, consider using a higher voltage system. A 480-volt system, for instance, will experience less percentage voltage drop than a 208-volt system for the same load and conductor size. This is because the current is lower at higher voltages for the same amount of power delivered. Fifthly, ensuring proper connections is crucial. Loose or corroded connections can increase the resistance of the circuit, leading to increased voltage drop and potential overheating. All connections should be properly tightened and protected from corrosion. Sixthly, balancing the loads across the two hot legs of the three-wire system helps to minimize neutral current. When loads are evenly distributed, the neutral current is reduced, which in turn reduces the voltage drop in the neutral conductor. Seventhly, consider using parallel conductors for large loads. When multiple conductors are run in parallel, the current is divided among the conductors, reducing the current in each individual conductor and thereby reducing voltage drop. The NEC specifies requirements for paralleling conductors, including the need for equal length, conductor size, and termination methods. To accurately calculate voltage drop, several factors must be taken into account. Firstly, the length of the conductors must be known. This is typically measured from the source to the load and back to the source for a single-phase circuit. Secondly, the current flowing through the conductors must be determined. This can be calculated using Ohm's law or by measuring the current with an ammeter. Thirdly, the impedance of the conductors must be known. This can be obtained from conductor tables or calculated using the conductor's resistance and reactance. The resistance can be found in NEC Chapter 9, Table 8 for alternating current resistance and reactance for conductors. The voltage drop can then be calculated using the following formula: voltage drop equals current multiplied by impedance. For a single-phase circuit, the formula is typically expressed as voltage drop equals 2 times current times impedance times length, where length is the one-way distance. Several online voltage drop calculators and software tools are available to simplify the calculation process. These tools typically require the user to input the conductor size, length, current, and voltage, and they will then calculate the voltage drop. It's important to note that the NEC provides specific requirements for conductor ampacity based on the termination temperature ratings of equipment. Section 110.14 C1 of the 2020 NEC, for example, specifies that conductors must be selected and installed such that their ampacity corresponds to the lowest temperature rating of the terminations, conductors, or devices involved. This is crucial for ensuring that conductors are not overloaded and that voltage drop is minimized. When dealing with existing installations, troubleshooting voltage drop issues can be challenging. Firstly, it's important to verify the voltage at the source and at the load. This can be done using a voltmeter. If the voltage at the load is significantly lower than the voltage at the source, then voltage drop is likely the problem. Secondly, check for loose or corroded connections. These can be identified by visual inspection or by using a thermal imager to detect hotspots. Thirdly, measure the current flowing through the conductors. This can be done using an ammeter. If the current is higher than expected, then there may be an overload condition or a short circuit. Fourthly, use a voltage drop calculator or software tool to estimate the expected voltage drop based on the conductor size, length, and current. If the actual voltage drop is significantly higher than the calculated voltage drop, then there may be a problem with the conductors or the connections. Voltage drop calculations are essential for ensuring proper system performance, preventing equipment damage, and complying with electrical codes. Understanding the factors that contribute to voltage drop and the methods for mitigating it is crucial for electrical engineers, electricians, and anyone involved in the design, installation, and maintenance of electrical systems. The considerations about balancing load, conductor size, length of runs, good connections, using copper instead of aluminum if possible, and possibly increasing voltage are key areas of focus.